Okay, good evening. Welcome to the January meeting for Silicon Valley ACM SIGGRAPH. Tonight, we will have an exciting presentation by Kenji Enomoto from Adobe Research, who will present some of his latest research in the area of image and video matting techniques. I am Alesh Jankarik, Chair of Silicon Valley ACM SIGGRAPH. Before we get to tonight's presentation, let me tell you about our chapter. Silicon Valley SIGGRAPH is an organization for graphic professionals in the Silicon Valley area. We typically try to host a meeting on graphics-related topics about once a month. Silicon Valley SIGGRAPH has been meeting in different Silicon Valley companies such as NVIDIA, Intel, and Google for many years. However, since COVID hit, we have moved our meetings online. This year, we would like to return to in-person meetings and are looking for locations where we can meet again. Typically, this requires for an employee of the host company to sponsor the meeting. If having Silicon Valley SIGGRAPH at your company sounds interesting to you, and you would be willing to help us out by sponsoring us, please contact us. Our contact information will be in the next slides. Now let me introduce the officers of our chapter. I am Alesh Jankarik, and I'm the chair of the chapter. Brent Simon is vice chair. Carl Anderson is the treasurer. Sharon Yang is secretary. And Ken Trukowski is a member at large. And finally, this could be you. We are always looking for more volunteers, and we need help in many areas of the chapter. In particular, right now, as I mentioned, we are looking for venues for in-person meetings. So if you could help with this, please contact us. You can find more information on our chapter on our website or on our meetup. You can also email us at this email address. We also have a YouTube channel where many of our events are recorded. To find this information later, just go to Google and type in Silicon Valley SIGGRAPH. If you're watching this on YouTube, these contact information will be in the description. Now I would like to introduce tonight's speaker. Tonight, we will hear from Kenji Enomoto talking about his research in image and video matting techniques. Kenji Enomoto is a research scientist at Adobe Research in San Jose, where he works on computer vision and machine learning. He is particularly interested in emerging devices that push the boundaries of research. He received a PhD in information science from Osaka University, Japan in 2022. So now please welcome Kenji Enomoto.
Thank you for the introduction, Alesh. I am sharing my screen. All right, let's get started. Hi, everyone. I'm Kenji from Adobe Research, and thank you, everyone, for joining us today. And today, I'm going to talk about massive and high-quality RGB alpha dataset. I'm so excited to talk about it today. So, first of all, what is RGB alpha image or video dataset? Some of you may know because it is supported in some image format like PNG, but the only image we usually use is just a simple RGB image, and the additional alpha channel represent the opacity of the subject. And it is useful to represent some motion blur, optical blur, transparency of the object. And it is necessary information. Alpha matte is necessary information to composite such a scene onto a new background. And today I'm going to talk about why we need such kind of data and how to collect such RGB alpha image or video data in high quality. And these RGB alpha videos I'm showing now are collected by our recent method I'm going to talk about later today. So let's jump into the introduction of this talk. First, what we can capture with a normal camera is an ordinary RGB image without any mask or alpha channel. And object masking is a very common technique in the computer vision or computer graphics field as a first of many of image or video editing. And this photo is from my Grand Canyon visit. And in this example, I put a text behind myself, which is a common way to emphasize a main subject of this image, like myself. And to do this, I had to segment out myself using, for example, the object selection tool in Photoshop. So literally, I used the object masking tool for doing this image editing. And this right-hand side example is Project Stardust from Adobe, which enables us really intuitive and interactive image editing. If you grab a subject in an image, you can move it to anywhere you like in the image. And the occluded background is filled out without doing anything. It's fully automatic way. And in here, object masking is used as the first step of this application. Then let's consider this case. Let's say you want to put a text behind transparent object like this wine glass. But if you do the same thing as I did for my Grand Canyon photo, it won't work as expected like this. What I wanted to do is I wanted to see the text through the wine glasses, right? So why it didn't work as expected? It is because the object mask is represented as a binary mask, meaning that the mask only has 1 or 0 value, representing the foreground or background respectively. And it cannot represent the semi-transparent pixels. So we need a new type of mask representation, and the primary candidate is alpha-matte or alpha channel of RGB alpha image. The alpha-matte value is the continuous value from 0 to 1, and it represents opacity for each pixel. And 1 means completely opaque, and 0 means completely transparent, and intermediate value represent the opacity of that pixel. And the problem of estimating the alpha matte or alpha channel of the image is called matting. And for most of the applications of the matting, the foreground color needs to be estimated as well because it is necessary to composite that subject onto a new background. And the matting problem can be formulated as an inverse problem of image composition process. And an ordinary image I can be considered as a result of composition of foreground F and background B. And the coefficient is called alpha. And it is written as alpha times foreground color plus 1 minus alpha times background color. And in this equation, alpha matte value, foreground color, and background color are usually unknowns. And writing this equation in the bottom vector form reveals that there are 7 unknowns, but we only have three equations. So the matting problem is known as a highly ill-posed problem. And a typical way of reducing this ill-posedness is to constrain the background, like chroma keying, using a green background as a player. However, even if the background is completely known, we still have four unknowns, alpha matte value, and three foreground color parameters. So, naturally, the ill-posedness of the problem motivates us to take a learning-based approach using neural networks. And in fact, several types of learning-based image matting methods are proposed, as shown here. For example, one approach takes a trimap as additional input to reduce the ambiguity. The trimap has three values representing complete foreground as white pixel and complete background as black pixel, and unknown pixels by gray pixels. And unknown pixels could be foreground, background, or partially transparent pixels. That's why it's called unknown pixels. And the trimap is the most informative input, but it is often really hard to make the trimap. You can easily imagine it's tough to make this trimap for many images. So recently, binary mask guided matting or visually promptable matting are proposed, which is way more easier to use. And in fact, the recent learning-based method is doing a really great job. The diffusion matting model proposed at the last ECCV is doing really great job on the hair details. And in another example, it's doing amazing job on the details of the branch. You can imagine that if I want to do the same thing with this model, it should take really long time to annotate this kind of alpha matte. But there's no perfect learning-based method, and learning-based method has always challenging cases. And I wanted to segment out this arm, hand, and this powder. And I made this trimap, but the result looks unsatisfied because this red lesion looks like the powder, but it is recognized as the background or, transparent pixels. I know this is really difficult case for matting or even for segmentation. However, there is definitely a demand for editing this kind of images. And also in this example, I wanted to estimate the alpha matte for motion blur plot. But looking at this result, this is very typical failure case of the matting, but this alpha matte is affected by the background texture, and we can see some flaws in the alpha matte estimate. So there's many of image matting model, and also, of course, there's learning-based video matting model. The common guidance for a learning-based video matting is trimap for every frame. But, it's really difficult to annotate the trimaps for every frame. It's not practical. So recent methods propose to use only one trimap for the first frame of the video. And also another research thread proposed to use binary mask for every frame. And this binary mask can be obtained from the video segmentation models. So it is way more practical than the full trimap program setup. And this is some quick result of very recent video matting model proposed in the last year. But unfortunately, you can see some flaws in this result video, and a background guy is recognized as the foreground in some frames, and looking at the details, the boundary is a little bit blurred, but getting detailed boundary is one of the major motivation of using the matting or segmentation. And in my opinion, I have never seen production-ready video matting model. And in this example, looking at the head of this woman, we can see some flickering. And this kind of temporal consistency is really serious problem in the video matting problem. And exactly, the matting has many advantages over segmentation. But unfortunately, in some cases, the segmentation will be the best choices to use, particularly for opaque object, because of its stable result. So why is the matting models so far behind the segmentation? There are many learning-based matting methods proposed since the explosion of the neural net. And the most recent diffusion-based matting model shows great capability of doing matting task. And in my opinion, like I said, there still needs more advancement in the video matting. But overall, the model is getting better and better, and matting model exploration is actively conducted in the research field. However, I feel the serious problem is the dataset. This is a list of commonly used image matching dataset. And the total number of the training dataset is around 80,000 images, which is a very limited number for image recognition problem. As you know, ImageNet for image classification program has much more images, and recent image segmentation model trained on millions of images. For example, recent segment anything model proposed by Meta published more than 11 million images. And people says sometimes it is not still not sufficient. So the matting model, the training data for matting model is very insufficient, and the matting model is at a serious risk of overfitting or limited generalizability. And unfortunately, the video matting dataset is further limited. The total number of commonly used video matting dataset is around only 700. But recent video segmentation models are trained on tens of thousands of videos. And recent segment anything 2 for video segmentation task just published more than 50K videos. And I know the annotation of the alpha is way more difficult and time-consuming than the segmentation mask. But if we want to build some successful model by a supervised learning, we have to build a large-scale matting dataset in any ways. And in addition to the data quality problem, the quality of the matting data may have some problems. And this example is from a video matting dataset. And this is annotated by a chroma keying using a green screen. And you can see the blurred far, and which I think should be more detailed and crisp details. And on the edge of stuffed animal, you can see the clear white edge, which I guess caused by color decontamination to get rid of the background color from the edge. And this another example is from another video matching dataset. And you can see the artifact on the hair, like JPEG artifact, and again, the white edge on the boundary of the subject. And in summary, we have a huge challenge on the quantity and quality of the dataset in the matching program. And we have to make much more efforts on the dataset in addition to model exploration. So let's get back to the title of this talk, how to obtain massive and high quality alpha matte. In other words, how to annotate the alpha matte so efficiently and accurately or stably. Of course, primary candidate of doing that is chroma keying. This is a de facto standard way of keying out a foreground subject from a green screen. And we can see very nice keying result in some movies because VFX professionals spend tons of times on doing chroma keying manually. But it is not efficient enough for massive dataset creation. And as shown in the existing dataset, the keying result could have some errors, and the result could be subjective because it's manual operation. So we want to think of analytical way of doing matting in a fully automatic way. And I'd like to first introduce triangulation matting. This is a promising way for extracting the alpha matte and foreground color of a subject. And the capture setup is really simple, a camera and target object and some display like TV. And this method pre-captures two background images with different colors, typically black and white like this, capture the black image and white image. Then the subject will be captured 2 times with the same black and white background like this. Yeah. And let's say the image is black background is I0 and the image with the white background is I1. And these images can be written in this compositing equation. The foreground color is shared, and in this setup, we know the background color. So the unknown is only alpha matte value and foreground color, and meaning that we have only two unknowns, and we have two equations. So the alpha matte value can be calculated in this really simple manner, and foreground color may be better to be extracted from I0. And this triangulation matting is very simple and stable, but this method requires to capture the foreground subject multiple times, at least 2 times, with black and white background. So this method works only for static scenes. So this method would be the best option for image matting dataset creation, although this method cannot capture the motion blurs. But for video matting dataset creation, we have to consider another way of doing matting. And I'm going to introduce another really nice way of doing matting, which is called sodium vapor matting. The sodium vapor matting requires a special background emitting a very narrow spectrum orange light, which is called sodium vapor light. And this method needs a special camera setup. This is the beam splitter, so that two cameras can capture the images with the same optical axis. And each of the camera has the filter, and red filter only blocks the sodium vapor light, and blue filter only pass the sodium vapor light. And if this capture setup capture the sodium vapor backlight, then the captured image will be like this, because one filter completely blocks the sodium vapor light. One image will be black, and another filter pass the sodium vapor light. So this camera can capture the sodium vapor light from the background. And if we capture the foreground subject with this setup, the captured images will be like this. One filter only blocks the sodium vapor light. So this camera can capture the appearance of foreground subject as it is. And another filter only pass the sodium vapor light. So most of the light from the foreground will be blocked. So the foreground appearance in this I1 will be nearly black. And these images can be written in this form. I0 has ordinary compositing equation, but in image 1, there is no foreground appearance. So this property allows us to compute the alpha matte in this simple manner, and foreground color can be calculated in this simple manner. And best point of this method is this is applicable for dynamic scenes, because these two images can be captured in a single shot. So this method can be used for video mapping dataset creation, and of course, image mapping dataset creation as well. And a drawback of this method would be the requirements of the special background and special camera setup. And most importantly, a foreground subject could reflect the light with the same wavelengths with the sodium vapor light. And if that happens, it affects the alpha matte quality, because this formulation assumes there is no foreground color in the image 1. And the sodium vapor matting was originally invented in 1960s. And recently, Paul Debevec re-implemented this sodium vapor matting using modern devices. And if you search for sodium vapor matting on YouTube, you'll find some interesting videos Paul did. I highly recommend watching them, by the way. It's really interesting. And the middle image of this figure is a proof of the drawback I mentioned. You can see the texture of the clothes. Ideally, this foreground subject is supposed to be completely black, but it is not. This means the foreground subject or this clothes reflect the light with the same wavelengths with the sodium vapor light, which breaks down the theory of sodium vapor matting. And the last one, the latest method of this research thread is magenta green screen. This method works in a very simple way. The foreground subject is captured against a green background under strong magenta lighting. Magenta, it only has the red and blue light, and there's no green color. And under the magenta lightings, this method assumes the red and blue channel of the foreground color can be observed by camera, and green channel will be gone. And this method also requires the pre-capture of the background like this. And let's capture the gray subject. Even if the subject is in the gray color, the captured image will be a magenta color because it is under strong magenta lightings. And the compositing equation for each color channel can be written in this form. Red channel and blue channel has normal compositing equation, but in the green channel, there's no foreground appearance in theory. And this observation allows us to compute the alpha matte value in this simple way. But there's no clues for recovering the green channel of the foreground color. So they propose to use machine learning colorization approach to recover the green channel from red and blue channel of the foreground color. And this work was also done by Netflix, although this method needs to solve ill-posed colorization problem using machine learning. This method would work well for dynamic scenes, at least as far as I observed in their project page. So roughly speaking, the computer vision or computer graphics can be said a research of the light. And I'm always thinking about the light, how the light propagates, how the light is reflected, and how the light is observed. It will be a source of research idea. And triangulation matting is leveraging the intensity of the light. And sodium vapor matting leverages the wavelengths of the light. And magenta green screen leverages both of the intensity and wavelengths of the light. And here, the light has one more feature, which is called polarization. So why don't we leverage the polarization of the light for matting task? And this was the beginning of our recent proposal. And there's actually very classic work for matting using polarized screen. This work uses a bright background with a polarizing filter. So the backlight is assumed to be completely polarized. And the scene is captured by two cameras through a beam splitter again. And each of the camera has two filters, two 90-degree shifted polarizing filter. One filter is 90-degree rotated from the polarizing filter of the background, and one filter has the same direction with the background polarizing filter. And in this setup, one polarizing filter completely blocks the polarized backlight, and one filter completely passes the polarized background backlight. And if the foreground subject reflects unpolarized light under unpolarized illumination, it looks the same for these two cameras. So if the background is captured by these cameras, then captured images will be like this because one filter blocks the polarized background and one filter passes the polarized background. And if the scene with the foreground subject is captured, the images will be like this. the foreground appearance is the same across these two images. And the compositing equation for these two images will be written in this manner. And this is quite similar with the triangulation matting. So the alpha matte can be calculated in this manner, as well as the foreground color. But this method has a similar concern with the sodium vapor matting, which is that the foreground subject could reflect the partially polarized light. The ideal compositing equation for this classic parametric matting is written in this form because foreground reflection is assumed to be unpolarized. The foreground color F is identical for any polarization angle. But real compositing equation should be written in this form. Foreground reflection is partially polarized, and F is intensity of unpolarized light, and P is intensity of polarized light, and theta F is angle of polarization of the foreground refraction. And substituting this real compositing equation into this alpha matte calculation, it gives the deviation of the estimated alpha matte from true alpha matte. Alpha t is the estimated alpha matte from a classic parametric matting, and alpha is true alpha matte. So indeed, if the foreground reflection is completely unpolarized, which means P is 0, the alpha t is always equals to true alpha. But if the P is non-zero value, or this cosine term is non-zero, then the estimated alpha matte will be deviated from the true alpha matte value. And in fact, this kind of error can be observed in real world. This knotted pixel should be the completely foreground, but the estimated alpha matte value is less than 1. So this issue is the main motivation of our recent work, which is presented at the CVPL last year. So finally, let's jump into our recent work. First, we redefined the parametric matting program with a modern color polarization camera. Modern color polarization camera has this color polarization RA filter on the camera sensor. Normal RGB camera sensor has a Bayer pattern RGB, but color polarization camera has 4 polarizing filter for each color cell. And this sensor enables to capture 4 color images at 4 polarization angles in a single shot. So in total, it's going to be 12 channels images. And if I capture the background with this camera, the captured image will be like this because background is completely polarized. One filter completely blocks the polarized backlight, and one filter completely pass the polarized backlight. And if we capture the scene with foreground subject, the captured image will be like this. And our basic strategy is that given 4 pre-captured background images and 4 target scene images or video, we first estimate high confidence alpha matte, because some pixels has errors in the estimated alpha matte, as I explained. So we first detect which pixel has the error and which pixel has no errors. And next, we encode these polarization images into spatial context, which we call parametric matting Laplacian. And we're going to use this parametric matting Laplacian to propagate the high confidence alpha matte into our remaining pixel. And finally, we get the complete alpha matte. And first, I'm going to estimate high confidence alpha matte. And our method begins with the real compositing equation. And we first convert the polarization images into Stokes parameters. This is commonly used parameterization in the parametric vision field, and this makes the analysis of polarization images much easier. And good thing is this cancel out the unpolarized term, which reduces the degree of freedom of this problem. And in this problem, we want to estimate all the red parameters, but if P is a free parameter, this foreground term can approximate the given image intensity without this background term. So we have to constrain some parameters. So we basically assume that the foreground reflection is partially polarized, but we assume the amount of polarized light is small. So we formulated the objective function as the minimization problem of the foreground intensity P, or alpha P. And this minimization problem can be written in this beautiful form without this theta f anymore, because we are using cosine squares plus sine squares equals 1. And this minimization problem is just a simple least squares problem with respect to alpha. So we can solve this problem very easily. And by solving this problem, we get the estimated alpha matte, and we get the minimized polarized foreground intensity alpha P as a residual of this least squares problem. And looking back to the source of the error in the estimated alpha matte, the polarized foreground reflection was the source of the error. And this minimized polarized foreground intensity is kind of lower bound of polarized foreground intensity. So thresholding this minimized polarized foreground intensity give us high confidence alpha matte. And this red pixels means ill-posed pixels in this problem. And the intensity of the polarized foreground reflection is a clue of finding high confidence pixels. And another clue is polarization angle of the polarized foreground light, which give us additional high confidence alpha matte. And we compute the angle of polarization for the given image and pre-captured background, and compute difference of the angle of polarization. And we simply threshold this difference of angle of polarization to get another additional high confidence alpha matte. because if the angular polarization of a given image is sufficiently different from angular polarization of the background, that pixel is likely to be foreground. And combining these two high confidence alpha matte result in the final high confidence alpha matte. And next, let's think about how to propagate the high confidence alpha matte into the remaining pixel. Today, I'm not gonna jump into the mathematical details, but I'm gonna explain the abstract of our idea. And a good way of propagating non-alpha matte into the remaining pixel is using matting Laplacian. The matting Laplacian begin with assuming the alpha matte can be computed by simple linear transformation of image intensity. And this coefficient parameter A and B is unknown parameter, and they propose to minimize this equation across for every pixel in the small patch and every patch across the image, and they proved this minimization problem can be summarized into this simple form. And here unknown parameter is only alpha matte vector. This is vectorized alpha matte for all the frame, all the pixels. And this matrix is called matting Laplacian. And we can compute this matting Laplacian only from the image intensity. So we don't have to concern about coefficient parameter and bias parameter anymore. And we employ this matting Laplacian idea, but instead of using the image intensity, we use Stokes parameters, which is enabled by using the polarization images. And we take a similar approach, and we get the similar matrix, but having different property. And we call this matrix parametric matting Laplacian. And we're going to use this matting Laplacian to propagate the high confidence alpha matte into ill-posed pixels. And our final objective function will be like this. The first term is about matting Laplacian, and second term is to enforce the alpha matte at high confidence pixels will be the high confidence alpha matte after this optimization. And the last term is just a matrix form of the least squares problem of the initial alpha matte estimation. And with this term, our solution will be the same with the classic parametric matting method, even in the worst case, like there's no high confidence pixels in the image. I'm not gonna jump into the mathematical background of this idea, but let's see how our parametric matting Laplacian improves the original matting Laplacian. Now, looking at this matting Laplacian objective, the smallest eigenvector of this matting Laplacian should be the solution of the problem. So the small eigenvectors should tell us something. And here is three smallest eigenvectors from original matting Laplacian and our matting Laplacian. And you can see our matting Laplacian captures the shape of the alpha matte more correctly than the original matting Laplacian, like this horn part. This is because the original matting Laplacian is computed based on the image. So the original matting Laplacian is affected by the texture of the given image like this. But our parametric matting Laplacian is less affected by the texture of the image. So this leads to more promising final alpha matte results. And finally, the optimal alpha matte can be obtained by solving this objective function, and it propagates the high confidence alpha matte into ill-posed pixels like this. And this objective function may look complicated, but it is just a least squares problem, and we can derive a closed form solution for this objective. And in summary, our method takes polarization videos of a target subject and pre-captured background polarization images, and we estimate alpha matte and foreground color of a target subject. And this can be composited onto the arbitrary background. So our method may be the best way of collecting RGB alpha image dataset or video dataset. And let's see several results of our proposed method with a comparison with classic parametric matting. And you can see the estimated alpha mattes of the classic parametric matting has some errors on the foreground because of the partially polarized foreground reflection. But our method improved that error. Like this. And this is another example. You can see some flaws on the middle alpha matte. And our method offers nice foreground alpha matte and also nice hair details or motion blurs. And this is another comparison with learning-based method, assuming a perfectly known background. And sometimes learning-based method fails really largely. So it is not suitable for dataset creation. And you can see another nice motion blur result in our alpha matte. And this is another comparison with learning-based method. And our method provides really temporary, consistent, and beautiful hair details. And this is more results. The left-hand side is one of the polarization image videos, and the middle is estimated alpha matte, and the right-hand side video is composited video onto green background. You can see some hair details, and you can see the nice motion blur here. And you can see crisp hair details in this example. And lastly, you can see the motion blur of this funny object. All right, this is all of my presentation. Thank you for your attention. Yeah, if you have any question, feel free to ask me.
I have a question about the, I think it was slide 48. There, seemed like the light bouncing off the guy's head
Wait a
was
second.
more transparent. Slide 48, I think. Is that right?
Okay.
Back
Let's
to you.
48. This.
One more. It's pretty tiny there. So
Yeah.
back another one.
Is this 48?
Go back another one.
Okay.
Another one, another one, another one. It's to the guy. There he is.
Mhm.
So you have spots on his head
Mhm.
for, is that somehow picking up polarization, reflecting off, or how is that?
You mean around
Yeah,
this part?
and
Yeah.
on the other one too. Yours even has it.
Yeah,
Yeah.
yeah, yeah.
Yeah.
We can see some, yeah, tiny flow on the head. And this is because uh the specular highlight here, and even under unpolarized light, the specular reflection causes the strong polarized light. So yeah, this error is because the polarized specular reflection. And yeah, our method is mitigating that issue, but yeah, it is still not perfect. And yeah, we can still see some, yeah, errors on that strong polarized reflection.
But very impressive there,
Thank you.
and great coverage, a history of all the methods of compositing there. Thank you.
Thank you.
I have a question about cost. How
Mhm.
much computation does it take per frame? And is it possible to use the results from one frame in order to speed up the computations for the next frame?
Currently, this is perfectly per frame methods. So the the computation for the previous frame cannot accelerate the computation for the next frame, but it is completely parallelizable. So you can process each frame in per if the, let's say, for the offline application. But yeah, like you said, this currently this method takes some time. Like for a single frame, it takes more than 1 second. I forget the exact number, but yeah, currently this method cannot be operated in the real time. That's, yeah, one of the future work.
Is that making use of the GPU or only CPU?
Exactly. This can be implemented in the GPU. Yeah. And yeah, it's really accelerates the uh, computation in theory, but yeah, we haven't implemented it in the on the GPU. We just parallelize this method using tons of CPUs because recently, yeah, no one is using CPUs.
Thank you.
Thank you. Yeah, and all of the contents I showed today is all published already. So yeah, if you come up with some questions later on, I'm happy to talk about that in email or LinkedIn message, X, whatever you want.
So is the future work just trying to improve performance then, like Ken was talking about?
Yeah, efficiency is one of the future work. And also, like I mentioned, this is perfectly per frame method at this moment. So the quality of AlphaMatte could be improved by considering temporal information. So this is that is, yeah, another feature work. And of course, yeah, the primary feature work is collecting RGB alpha dataset using this kind of technique.
So a general question about creating a data set.
Yeah.
How do you know you have good coverage of what people need in terms of, for training? At that?
It's yeah, it's great good question, and it's kind of, yeah, tough question. Honestly, I don't know what number is enough for uh uh matting model training, but at least matting problem should be more difficult problem than image segmentation or video segmentation. And recent segmentation model is getting better and better, but there may be still challenging cases, even trained on millions of images. So I guess, yeah, at least we need same amount of data set with segmentation, but yeah, I know it's a lot.
But a particular production could have people in their outfits and settings and all that so the set would be highly matched to, let's say, the movie they're producing, right?
Yeah, for example, chroma keying.
Well, I just meant in terms of what objects are in the scene and such. It could learn. People could be on the set for a few days or something on this set, and then use it for learning in the other environments, right?
Yeah. In such case, yeah, some paper reported dramatically small set of data set is enough for learning a model for such specific task. And yeah, what I remember is just using it was about 3D recovering paper, but that paper said several tens of people portrait data was enough to learn such a specific 3D recovering task. So yeah, I think yeah, general mapping task requires tons of data, but such specific task only needs really small data set, I think. So yeah, it depends on the use case, but yeah, I have seen such observation.
Thank you very much for the presentation. It was very interesting, and hearing this,
Thanks.
I'll have to watch it again to pick up
Thanks so much. Yeah,
details
thanks so
there
much
from the
for
formulas.
yeah, I've tried to get rid of equations as much as possible, but yeah, this paper tends to, yeah, is lean to theoretical aspect, and yeah.
So yeah, I should go back to the paper too, right? That might be better
Yeah,
for,
thank you.
for the details. But yeah, it's good getting the broad overview here too.
Yeah, Kenji, thank you very much for coming to present
Thank you
to
for
tonight's
having me
meeting.
today.
Yeah.
Yeah.
Okay, if there's no more questions, maybe we'll uh, end it here. Let's-
Thank you, Kenji.
Thank you so much. Great to see you today, everyone.
Okay, thanks again for coming to the meeting today.
Thank you so much. Yeah.